जिस तरह हमने अभी उसमें ट्रस डिज़ाइन में किया, उसमें ये है कि बाज़ औक़ात हमारे कुछ सेक्शन जो है वो कॉलम सिलेक्शन टेबल में नहीं होते, लेकिन प्रॉपर्टीज टेबल से अगर हम उन पे ट्रायल करें तो वो सिलेक्ट हो जाते हैं। लेकिन सर पेपर में तो इतना टाइम नहीं होता कि बंदा ट्रायल करे। तो
नहीं होते, मैं आपको
सर वो 1-2 सिलेक्ट हुए हैं,
नहीं
मतलब
नहीं
कुछ
नहीं
और
नहीं
बच्चों के भी हुए हैं और मेरे भी।
इशू है ना, इसलिए मैं आपको बताता हूँ कि जोन से कॉलम सिलेक्शन टेबल में सिर्फ वही कॉलम दिए गए हैं जो कि लोकली स्टेबल है। वही बात की, ठीक है।
यस
तो
सर।
बहुत कम चांसेस है, उसका एक इशू है क्योंकि उसमें बड़ा केयरफुली जो है ना वो कॉलम सिलेक्शन टेबल वो डिजाइन किया गया। अगर एक कई सेक्शन होंगे तो वो मार्जिनल डिफरेंस होगा उनका, समझिए।
यस सर, वो ये है कि 200 की बजाय 198 स्लेंडरनेस रेशियो या 99 इस तरह से भी जाके वो
हाँ
सेटिस्फाई
जी, हाँ
कर।
जी, हाँ जी, हाँ जी। क्योंकि वो एक्चुअली आप सेलेक्ट कर सकते हैं उधर से भी, लेकिन जो कॉलम सिलेक्शन टेबल हैं वो जस्ट दे आर टू फैसिलिटेट द स्टूडेंट, ठीक है, ताकि उनकी सिलेक्शन जो है वो इजी हो जाए,
यस सर।
ठीक है। लेकिन
यस
मेरा
सर।
अपना ज़ाती ख्याल है कि कॉलम सिलेक्शन टेबल में सिर्फ वही सेक्शन दिए गए हैं जो कि लोकल स्टेबिलिटी का क्राइटेरिया भी पूरा करते हैं। सिर्फ आपने स्ट्रेंथ क्राइटेरिया ही चेक नहीं करना, लोकल स्टेबिलिटी भी चेक करनी
सर
है।
वो सारे क्राइटेरिया चेक
हाँ जी।
किए थे।
नहीं, एक इसमें एक और चीज़ है जो कि आप जब मिड टर्म के बाद आएंगे ना ऑन कैंपस, तो वहाँ पे मैं एक चीज़ एक्सप्लेन करूँगा कि AISC कहती है कि आपका कॉलम का क्रॉस सेक्शन एरिया जो है वो एक मिनिमम एरिया से कम नहीं होना चाहिए। इट शुड नॉट बी लेसर देन सर्टेन वैल्यू। इट्स मीन दैट फॉर एग्जांपल एंड दैट एरिया आई गेस इज as angle section 6.4 into 6.4 into 64 into 6.4, इसका जो एरिया सेक्शन का है उससे कम नहीं होना चाहिए। अगर उससे कम हुआ तो हमने वो वाले ही सिलेक्शन सेलेक्ट कर देना है। So there are some requirements that I will explain maybe when you are coming on campus in psychomotor classes. So I will also give you the detailed instruction how you can sketch the sheet. Yes, Moin, you have
Okay
any
sir.
question? Moin, please ask the question.
Yes, sir. Sir, I was solving the question about the double channel section, and it was said that we have to place it face to face. So we can't use, I think so, for face to face stay plates. Their gap was about 300 millimeters. So whether we can use a stay place.
Moin, sorry to interrupt you. Moin, I'm interrupting
No
you.
problem.
I'm
No.
unable to hear you because there is interruption in your voice. So would you like to write your question in the chat box?
Sure, sir. Sure.
Because I'm unable to hear you properly because there might be your end. Okay. So please write down your question in the chat box. So during break or at the end of the lecture, inshallah, I will respond your question. So Uzair, I'm going to share my screen, and please just let me know if you can see this screen. Uzair, can you see the screen?
Yes sir.
So is it visible? Uzair, please respond.
Yes sir, visible.
Okay. And also, can you see the screen, lecture slides?
Yes sir, lecture slides are also visible.
Okay. So just let me know because I'm having because your voice is having some interruption or distortion. So is there any distortion from my side also or not?
No sir, your voice is clear.
Okay, my voice is clear, but distortion is coming from your side. Okay, no problem. So let me start the lecture. And before starting, I would like to start the call. Okay, Bismillahirrahmanirrahim. Okay, dear student, today we are going to solve our second example, and that example is related with the design of intermediate stiffness. So we need to consider the same plate girder that we have proportioned in example 6.1. That we are given the span, we are given the loading, and we have already sketched the shear force diagram. So just I want to connect this design with proportioning of plate girder. So in proportioning of plate girder, what we have done, we have decided of length and side of the web. And basically, height of the web is a function of maximum bending moment and also the flange sizes, they are also the function of bending moment. Although we have selected thickness to satisfy the shear criteria, but we did not check the local stability of web because portioning of plate girder AISC allow us to select the cylinder web because in plate girder is always cylinder. Cylinder means it is very thin and it will always undergo elastic buckling. P over T ratio of the web, which is height of the web over thickness of the web ratio, it is more than lambda r, which is 161.2 in case of 836 steel. So it means that we did not check the local stability or the web shear strength in proportioning of plate girder. But now, in this second example, what we will do, we will check the shear capacity of web because we know the web size, which was 2300 millimeter in depth and 10 millimeter thick. So what we will do, we will check the shear capacity. Obviously, the web will buckle. Why it will buckle? Because it is because thickness is very small as compared to depth. So if shear capacity is less than applied, and where we are getting the applied shear from, this shear force diagram. So if the shear strength of the web or buckling strength of the web is less than applied shear, so in that case, we need to stabilize the web or we need to increase the shear strength of the web by providing the intermediate stiffener. So by using intermediate stiffener, what we are doing, we intend to divide the web into different sub-panels, and then by providing the stiffener, we can also achieve the tension field action, and due to tension field action, the strength is further improved after buckling. So how we may start? So we are using the same example, 6.1, and in that example, we have already given the beam length and the loading. And we have already sketched the shear force diagram and it is given over here. So it is subjected to maximum shear 1519 and then shear force is decreasing within the center span depending upon applied load. So actually when we are given the loading, so we already know the location of intermediate stiffener. So sorry, bearing stiffener. So we are going to design the two type of the stiffener. Number one is bearing stiffener and number two intermediate stiffener. Design of bearing stiffener we will learn in our topic, but for intermediate stiffener we have to carry out the design in this particular example. So we are already know the location of bearing stiffener because what is the function of bearing stiffener? Because they are actually resisting the concentrated force by providing the column action. So they are provided where we are having the concentrated applied force or force reaction. So force reaction, they are also termed as external forces or concentrated forces. So bearing stiffener are provided above this force reaction and underneath concentrated applied force to the web crushing or web crippling and to safely transfer this concentrated force to the web. So location of bearing stiffener is already given or already known. So we have provided, we know the location of the bearing stiffener. Two are acting at the ends above this force reaction and two exactly underneath the applied force. And one thing more, bearing stiffener, they serve as both the concentrated applied force and they are also serving as a intermediate stiffener. So they also fulfill the requirement of intermediate stiffener. So what we are supposed to do? Now we need to decide. So whether we require the intermediate stiffener in this or not, because we already know the location of the bearing stiffener. So what we do, we want to check the capacity, shear capacity of this web. if shear capacity of this web is less than shear, then we need to provide the stiffener. So just like we need to provide this intermediate. So what we do when we want to design intermediate stiffener. So we are having two objectives. Number one, what should be the spacing of intermediate stiffener, and what should be the size of intermediate. So in the first phase, we will decide the spacing of for intermediate stiffeners if they are required, and next we will decide the size of intermediate stiffener. And actually, in most of we provide all intermediate stiffener at equal spacing or uniform spacing. But ASHTO and AISC both, they suggest that first stiffener should be provided closer to bearing stiffener. Why? Because the ends, they are subjected to larger shear force. You can see that the shear force is maximum at the end and it decreasing when we are proceeding toward the center. So AISC says that we should always provide the first at closer to the bearing stiffener or at less spacing, and then rest of the stiffener which we are providing in the central span, that should be provided at maximum and uniform spacing. And also AIC say that because shear force is maximum at the end, so we are not supposed to consider tension field action for the first panel. Even though the tension field action will be available, but we want to ignore the tension field action to enhance the shear capacity or to using a larger factor of safety. So how we can, so actually you don't need to memorize the procedure because complete design procedure, it is provided LRFD design aid. So it was page number 324, I guess it was. So design flow is also provided. Yes, from the page number 293 on LRF design aid, you are having the design flow chart. So you can consider this design flow during examination also. So you have to follow this design flow, but I will explain that why are considered in this design flow. So when you are, I'm explaining this example. So I suggest you to open LRFD design aid and just compare the equation that I in this design example, because you supposed to consult this a design flow or LRFD design examination. Okay, I will explain my design. So actually you are quite familiar with this equation. In this design equation, the shear capacity should be more than applied shear. So what does it mean? If I want to design the, I want to decide the location of first intermediate stiffener in this panel, and will be somewhere here, and I want to know the spacing. So it means that I should know the shear capacity of this web panel. So this shear capacity will be compared with the maximum shear force which is subjected in this panel. So the maximum shear force will be the shear force at any point within this panel. So this panel is subjected to shear force of 1519. So applied shear is VU is 1519, and 5 EVN we are going to compare with the web capacity. So shear capacity is equal to 0.6 Fy, which is tau y, yielding capacity of web, height of the web into of the web and into CV. So we are ignoring CV prime because we do not want to consider in field action for the first intermediate step. So the first step is we need to check this case. Height of the web over thickness of the web ratio. It should be less than this parameter 0.46 under root E over Fy. You have been using this equation in hot rolled design. Because if height of the web over thickness of the web ratio is less than this parameter, then web never buckle. It will always fail due to the shear yielding. So in that case, CV value is equal to 1. But if this value is more than this factor, then web will always under buckling and CV value will be less than 1 because CV value will convert the shear yielding strength into the buckling strength or critical shear stresses at which the web will buckle. Okay, for the first intermediate stiffness, we do not want to use the tension field action. So VU will be 1519. Actually, we want to determine how much CV value is required to have shear capacity equal to VU. Because we know 0.6 Fy, we know the height of web, and we know the thickness of the web. So we want to determine how much minimum CV value is required in such a way that shear capacity should be more than VU. And actually, from this CV, we want to determine the spacing of first intermediate stiffness. So actually, we are interested in the A value. So actually, A over H ratio, if you are given the spacing design is already given, then you can determine the A over H ratio. And A over H ratio, if you know, you can determine the KV value. And depending upon the KV value, we can determine the CV value either using equation number 3 or equation number 4. So in other words, if we know the CV value, we can use either equation number 3 or equation number 4, equation number 4. If we know CV value, so then from this equation, we can determine the KV value because all the other parameters are known. Then if KV value, then by using this equation 5, we can determine the spacing. But the question arises that here, we can determine how much CV value is required by using this equation. So we want them in CV. So all these parameters, they will go to the other side and VU will be divided by all these parameters. So CV required is equal to VU into 1000 to convert this value into Newton, 5E 0.9, 0.6 Fy, the shear strength of the web and area of the web, and CV required is 0.489. So we need the minimum CV value 0.489 to match the shear capacity equal to V, or to increase the shear capacity of the web equal to more than applied shear. Okay, we got the CV value, but next question arises whether we need to equation 3 or equation 4 to determine KV value, because we got two equations. So actually this equation 3 and 4, they are depending upon these two conditions. So question number 4 is for elastic buckling and question number 3 is for inelastic buckling. So actually equation number 4 gives the lesser answer or conservative side or unsafe value, least value of KV. So we assume that first condition, height of the web over thickness of the web ratio is more than this parameter, because this parameter is the function of KV value. So KV value is unknown. So So we assume that height of the web over thickness of the web ratio is more than this value. So if we are assuming this, then by using equation number 4, we know CV value, so we can determine KV value easily. So this is the assuming this parameter because KV is unknown. So this is the equation number 4. Again, I'm showing this equation 4. So this is the equation of CV in terms of KV value. So by cross multiplication, we can represent this equation in terms of CV value. Equation of KV in terms of CV. So this parameter, when they will go to the other side, they will multiply with CV value, and 1.51 into E value will be dividing when they are going to the other side. So just like this. So to achieve CV value 0.489, we need the KV value 21.41. If KV value is coming out to be 5, so KV value 5, we have already studied that KV value 5 is for the cases if there is no intermediate stiffness. If we do not require intermediate stiffness, or if the stiffness they are provided at a maximum spacing, then KV value will be equal to 5. But if it is more than 5, then we need to determine the A value from the equation number 5. So first, actually we have determined the KV value. So you can recompute this parameter and you can verify the condition whether H over TW is still more than this parameter, because now you have determined the KV value. First KV value was unknown. So when you substitute the KV value 21.41 in this equation, 21.41 multiplied by E value, which is 200,000 or 2 exponent 5 megapascal, and Fy 250. So by solving this equation, answer is 179.3. And this parameter is less than 230, which is height of the web over thickness of the web ratio. It means that this condition satisfied. If this parameter comes out to be more than this, more than this parameter, may mean height of the web over thickness of the web ratio is less than this parameter, then in that case, you need to revise KV value by using equation number 3. Because if this condition doesn't satisfy, if this parameter comes out to be more than this parameter, then you need to revise KV value by using this equation number 3. Otherwise, already determined KV value will be final. So now we are using equation number 5 because we have determined the KV value. If you substitute the KV value here, the unknown will be A because we already know the H value. You can also represent this equation by this, because if you are bringing this 5 will, when it will go to the other side, it will be dividing. So that equation will become KV minus 5 over 5. So anyhow, by using this equation or by representing this equation in terms of KV value, so this is the same equation, just like equation number 5. So H value is known, or you determine the A over H value required. So you can represent this A over H required. So actually I should represent maybe so that to remove the confusion. That is the required value, and I will mention why I have represented required. So by solving this equation and substituting the H value 2300 and kV 179, sorry, 21.41. So by solving this equation, we are having A required 1.71. We need to compare this A required with A maximum. So A maximum by AISC says the maximum spacing of the stiffener should not be more than 260 divided by lambda W. Lambda W means height of the web over thickness of the web ratio whole square multiplied by H value. Or A over H ratio should be less than this parameter. So this is the same equation which we have already discussed. So A maximum. So A over H maximum should be less than 3 and A over H value be less than equal to this parameter. So we are using this expression. Because first intermediate stiffener, we don't want to provide this spacing. So we are computing what would be the maximum spacing by this equation. So A required is 1.27 and A maximum by AISC, substituting the values 2300 divided by 10 is 30. So 1000, we have divided the whole parameter by 1000 to convert the A maximum into meter. So maximum A value is 2.94. So we can this max spacing more than 2.94. So our A required is less than 1.27. So we shall use this value. If this value is coming out to be more than A maximum, then we will provide the stiffener at maximum spacing. So A required is, or what I can say that whichever is the lesser out of these two, that is the A maximum. So first stiffener should be provided at a maximum spacing 1.27. So spacing of first stiffener should not be more than 1.27. But we will provide at a spacing less than this value, maybe to bring to the a safe limit. So here we have selected the A value 1.2, a little bit lesser than this value. You may select 1.25 also. That will be perfectly fine. If in examination somebody he has taken this value 1.25 or somebody has taken 1.2, both are perfectly okay. So here in this example, A value is considered 1.2. But again, if you want, you may select 1.25 meter also. So we are providing the stiffener, first stiffener at a spacing of 1.2 meter. Okay, now we need to check the capacity. We need to check the capacity with this spacing. So if we know this spacing, we can easily compute the A over H ratio. If we know the A over H ratio, because 1.2 divided by 2.3, so we can compute kV value because kV value is function of the A over H ratio. If we know the kV value, you can compute this parameter. So this is missing over here. So if you compute this parameter, and if this parameter is less than 230, which is the height of the web over thickness of the web ratio, then you can use this equation number 4 to determine CV value. If actual height of the web over thickness of the web ratio is less than this parameter, but more than this parameter, then you're supposed to use equation number 3 to compute CV value, depending upon this parameter or your case. But in this given case, height of the web over thickness of the web with exact kV value is again more than this parameter. So you're supposed to use equation number 4 to determine CV value. So 1.51 kV, you just have determined E value 200,000 megapascal. Height of the web over thickness of the web ratio is 230 square and 250 yield strength of web. So the parameter is coming out to be 534. Okay, what does this CV value represent? This CV value represents that the web is buckling at a stress value 53.4% or 0.534 time of the shear yield value, or the web is buckling at a maximum stress value which is equal to 53.4% of shear yielding value. So in this case, we have decided the location of first intermediate stiffness. The first intermediate stiffness is provided at a distance of 1.2 meters from this edge. And similarly, we need to provide a stiffener also on the other side. So we are only designing the stiffener on the one portion, and the same stiffener will be provided on the other side, because we are having identical loading and symmetrical dimension for the plate builder. So we will design the stiffener on one side, and the same stiffener will be provided on the other edge or on the other end also. Okay, next we are having this panel now. Okay, in this panel, we need to check that whether we require the stiffener or not, because first stiffener we have provided at 1.2, just like here. So now for this panel, maybe we do not require stiffener. First, we need to check the capacity of the web without any stiffener. So what is the applied shear for this panel? We need to check that what is the maximum shear force within this panel. So the maximum shear force will be at this edge, at this point, which is at a distance 1.2 meters from this end. So we can determine from the shear force diagram 1519 minus 1.2 times of 76.9. If there is any student who just log in, Naveer Abbas, if you have just log in, so please feel free to talk. So we need to check what is the shear force for this second panel or for the other intermediate stiffness. So VU in this will be equal to maximum shear force will be at this edge, which is 1519 minus 1.2 of 76.9. So first, maybe we do not require stiffener. Maybe the shear capacity of zone is more than this applied shear. So we need to check this. So actually here in the previous, when we computed CV value 0.534, so we can compute the shear capacity 0.9 is the strength reduction factor, 0.6 is the parameter to convert the normal strength into the shear strength. Area of the web we know 2300 and multiply by 10. CV value we have just computed, so capacity is 1656.9, which is more than 1519, which is more than 1519, so it is okay. For the second intermediate stiffness, what is the VU? So VU at a distance 1.2 is 1519 minus omega into x is 1.2. And omega UDI load is 76.9. So VU applied shear for the next panel will is 1426.7. Okay, maybe we do not require this stiffener for the next panel. So what we will do, we would like to determine web capacity without intermediate stiffener. So in LRFD design aid, if we are not providing intermediate stiffener, so then KV value will be equal to 5. So KV value 5 is it exists in specification actual, but we have said that if we are not providing intermediate or we are providing this stiffener more spacing, KV value will be equal to 5. If we are using the KV value 5, then that will be giving the CV value for the shear capacity of web alone. So these parameters, they can be simplified for KV value equal to 5. In this equation, KV value equal to 5 and E value is 200,000. This 5 is 1,000. So 1,000 and 1,000, it means that you will have the answer 1 million. So if you are taking the under root of 1 million, that will be 1,000, and 1,000 is multiplied with 1.37, so answer will be 1370. So you can convert this parameter for KV equal to 5. So this parameter will become like this. So for KV value equal to 5, so this parameter, which is 0.37 under kV into E over Fy, if you substitute kV value 5 and E value 200,000, then this parameter will become this one, 1370 under E over Fy. So just check height of the web over thickness of the web ratio. It is more than this parameter. This parameter is same as of this parameter. Okay, so in that case, you need to use this equation to determine this CV value. So this equation can also be simplified for KV value equal to 5. If KV value is 5 and E value is 200,000, if you substitute KV 5 and E value 200,000 megapascal, so this CV4 equation, this equation number 4 will be simplified like this. So this is again equation number 4. So after substituting all the values of the web over thickness of the web and Fy, CV value is coming as 0.114. So what does it mean? It means that web is buckling at a stress value equal to 11.4% of shear yield value, or it is having the value, a buckling strength of the web is equal to 0.114 times of shear yielding value. So almost 89% strength we are, 89% strength we are losing, or we are not able to achieve because web is too slender or too thin. But anyhow, we are using this CV value to determine the shear capacity of the web panel. So 5V is 0.9, 0.6 Fy. We can substitute the value, area of the web 2300, and CV value we have placed. So this is the capacity 350 kilonewton. So this is the capacity of web alone. If we are not providing any stiffener, so the web capacity is 354. So web will buckle at a load of applied load 350. But applied shear is 1426. Less. So it means that the also intermediate stiffness for height of the web and thickness of the web, second condition are satisfied, which is less than 260. But if any wants to provide the intermediate stiffness. Okay, for the second intermediate stiffener, what we will do, first we will try to place this stiffener at a maximum spacing. We are using the iteration method, hit and try, because for the second intermediate stiffener, we also want to achieve the tension field action. So both tension field action formula, CV prime and CV, they are function of spacing of stiffener value. So first, we want to provide the stiffness at maximum spacing. We are having two formula for maximum spacing that we have also seen in LRFB design aid. One is A over H ratio equal to 3 and by other is by equating A over H ratio equal to 260 divided by lambda W value whole square. So if spacing is more than these values, so we will consider that even though the stiffness they are provided, so they are not contributing to the shear strength. So the A maximum is obtained from these two equations, and the lesser value out of these two equations will be our A maximum that we can provide. So these are the same equation, but H is going to the other side. So first A maximum we are determining 260 divided by height of the web over thickness of the web and multiplied by H. So this is 2.94. And second equation, A maximum is equal to 3H. So lesser answer out of these two is 2.94. It means that second stiffness we may provide at a maximum distance of 2.94. Okay, first we taken this 2.94. So we need to provide this 2.94. So we need to decide the stiffness in this panel. So how many stiffness are required? We can easily determine. For example, what is the distance from this intermediate stiffness to this very stiffness? 5.8. Because distance for very stiffness is 7 meters from the center of this stiffness. So 7 minus 1.2 will be 5.8. So 5.8 divided by 2.94. So we will determine that how many spacings we can provide, because if we are having one stiffness, spacing will be 2. So if we are having two spacing, it means that we may require only one stiffness over here. 5.8 divided by 2.94. So 5.8 divided by 2.94, which is a maximum. So we require at least 1.97 spacing. We will round to the upper side. So we require 2 spacing. So if the spacing is 2, so we require one stiffener only. So A will be equal to total length, available length divided by number of spacing. So we need to provide us this stiffener at this spacing of 2.9 meters. So what we are going to do, so we will provide the second stiffener at a spacing of 2.9 meters. And this is less than 2.94. So we need to provide the second stiffener at a spacing less than 2.94. So by using the available distance, we subdivided the available distance into 2, which is equal to 2.9. So now it means that second intermediate stiffness is provided at a spacing of 2.9 meters. Okay, now we need to check the shear capacity of this panel with spacing 2.9. Okay, now for this second stiffener, we can utilize the tension field action. So we need to determine the CV value and CV prime value, and we need to compute the shear capacity of this web panel, which should be more than our design or applied shear, which is 1400 and something value. What was the value? Which is 1426. So A is decided 2.9. If we know the A value, we can determine the A over H ratio, which is 1.26. From the A over H ratio, we can compute KV value 5 plus 5 over A over H ratio. KV value is coming out to be more than 5, 8.14. You can compute this parameter 1.37 under root KV into E over Fy. And this parameter is 116, which is less than 230 height of the web over thickness of the web ratio. So it means that this condition is satisfying because this parameter is less than height of the web over thickness of the web ratio. So you need to use equation number 4 to determine CV value. So equation number 4 is used to determine CV value. 1.51 into kV into E value divided by height of the web over thickness of the web ratio into F. So CV value is coming as a 0.16. And further, we want to achieve tension field action for the second panel. So tension field action will be considered. So CV prime value is computed by this equation. So this equation taking this equation, I need to correct it. There should be equal. So this equation is also given in LRM and the flow chart. So when we determine this CV prime value by substituting all the value, answer is 0.44. Now we will determine the shear capacity by using this formula 5V. So let me V 0.6 Fy area of the web CV plus CV prime, because now we want to use the tension field action also. 5V is 0.9, 0.6 Fy, web 20 into thickness of the web. CV value is 0.186 and CV prime is 0.44. Please understand one. Earlier I have explained that field action improve the strength almost 2 to 3 times more than critical buckling strength, or post buckling strength provided is almost 2 to 3 times more than the web buckling strength. So CV prime is the fraction or the factor which is letting us know the post buckling strength in terms of yield strength. So it means that buckling strength is almost 18.6% as compared to the yield strength. And post buckling means strength enhancement by tension field action is almost 44% as compared to the yield strength. Okay, just if we normalize, if we dividing this value also by 0.186, so this will be the 1. And if I also divide this value by 0.186, so 0.44 divided by 0.186, answer is coming 2.36. So it means that post buckling strength is almost 2.36 times more than initial buckling strength. So here, that was the explanation that we have already discussed earlier. The total shear capacity is coming 1943.7, which is more than applied shear. So that's satisfied. But in case, for example, in examination or in any problem, if this answer is coming less than VU, then what you need to do in that case, just reduce this spacing. If you have considered 2.9, You can make it maybe 2.6 hit and trial, but maybe you can reduce maybe 2.5 or 2.6. You need to see that how much is the difference between the capacity and applied shear. So depending upon the difference, you can reduce this A value maybe 2.9 to 2.5. You can again determine A over H value and CV value and CV prime, and then you can again recheck the capacity. So if the capacity is more than VU, then it is okay. If the capacity is still less, then you are keep reducing the A value, and by hit and trial value, you want to determine the maximum A value for which the capacity is just equal to or more than applied shear. Okay, next is now we have decided the spacing of the stiffener. So we are having one bearing stiffener here, which is also serving as a intermediate stiffener. Now we need to check whether we require any stiffener here or not in this second panel. So in this second panel, or sorry, in the middle portion, first of all, we need to see that what is the applied shear for this central portion. So in this central portion, so maximum shear is at this edge, which is 230.7. So applied shear is 230.7. So central span is having the applied shear 230.7. But what is the capacity of the web alone? We have just determined. So capacity of the web alone without stiffener is 354, which is more than applied shear. This means that we do not require any stiffener in this central portion. So X value, sorry, VU value at a distance 7 meter is 230.7. So that we have already seen from our shear force diagram, 230.7. So applied shear is this one. The shear capacity without tension field action or without stiffener is 354. We have already determined, which is more than VU, which is 270. .7. So it means that we do not require any stiffener for this center portion. And also height of the web over thickness of the web ratio is less than 260. So no intermediate stiffener are required. But again, AISC says that if we do not require the intermediate stiffener, it is better to provide the stiffener at a maximum spacing equal to 3H. However, if the length of the portion is greater than 3H, it is better to provide the intermediate stiffener at spacing not exceeding 3H. Because if the spacing of the stiffener is equal to or more than 3H, so it means that we are not providing any stiffener. So let's check what is the spacing of the central portion or length of central portion. Okay, length of this central portion is 6 meters from here. This portion is having the length 6 meters, which is less than 3H. So what is 3H? Because 3 times of the H, height of the plate girder is 2.3. So 3 multiplied by 2.3 is 6.9. Spacing is less than 3H, so we will not provide any stiffener. So in the first phase, we have computed the size of the spacing of the stiffener. So I will not have break because next phase is maybe just small portion. We just need to select the size of the intermediate stiffener. So I will continue because I will try to finish up the lecture earlier. So now in the second phase, we need to decide the size of the intermediate stiffener. So size of the intermediate stiffener is fixed by this AST minimum. So now I will keep on showing you this because I'm following this design flow. So I have already completed. Now I'm carrying out this size of the intermediate stiffener. So which is also mentioned over here. So we need to compute the AST minimum. So AST minimum or minimum area required for the stiffener from this expression. So this equation will give the maximum answer if CV value is lesser. So lesser CV value is for the interior segment. So it means that we need to determine the AST minimum for the first stiffener and for other intermediate stiffener. So whichever is giving the larger value, that is our AST minimum. So Fy is the yield strength of web. Fy is the FYST yield strength of the stiffener. If we are using same material for stiffener and web, then this ratio will be equal to 1. ds is the distribution parameter. If you want to provide intermediate stiffener in pair on both sides, then ds value will be equal to 1. Otherwise, this value will be equal to 1.5. Maybe we have already, sorry, 1.8 that we have already discussed. Maybe in our specification or design aid, we have already discussed. This might be mentioned. Yes. If you want to use single plate for stiffener only one side only, then this value is 2.4. But we want to provide this stiffener in pairs, so this value will be equal to 1. And what is the VR value? VR is applied shear or required shear strength, or VC is the capacity of the panel with stiffener. So VR is the required shear, which is equal to VU. So I will write down in bracket VU, which is the applied shear force that we have already considered in design. And VC is capacity. So however, VU and VI should be used for the same. So we need to compute 2 AST minimum for the first stiffener and for the second stiffener. So for the second stiffener, so for this, DR is the applied shear, which is 1426 for the second stiffener. 1426 is the applied shear, which is equal to VR, and what was CV value for the second stiffener? 0.186, and when we determine the capacity, and the capacity, it was 1943.7. For the second stiffener, VU applied here is 1426 and capacity is 1943 and CV value is 0.186. So AST minimum for the second stiffener is, by substituting the value in this equation, ds value 1, because we want to use the stiffener in pairs, height of the web and thickness of the web, CV 0.186, VR is VU applied shear for the second panel, VC is the capacity of the stiffener with second intermediate stiffener, and 18 time of the thickness of the web cube. So AST ASTM minimum is 261.4. So if you want to use the same equation for the first intermediate stiffness, for the first intermediate stiffness, CV value was 0.534 and applied shear is 1519 and capacity 1656.4. I will quickly show you these values. So applied shear for the first panel is 1519. CV value 0.534 we computed and the capacity 1656 for the first panel. So when we substituted this value, so our answer is almost zero. So it means that AST minimum is coming critical or larger from for second panel, which is 261.4. Actually, I have already explained this equation when we proportion the flange of the plate builder. So B over T ratio of stiffness should be less than equal to 15. So by using this equation, if we multiplied it B and also divided the same equation by B, so this will be B square and B into T is equal to area. So if we are bringing the area to the other side, actually we want to determine the size of two stiffeners. So that will be multiplied with 2. Because we want to provide these two stiffeners. So that's why this equation multiplied by 2. So 2 is dividing on the both sides, that will become 7.5 B square into AST minimum. So if we want to determine the width of one single stiffener, that will be 7.5 times of the AST minimum that you have just determined. So by using this equation, we have determined the BST minimum and answer is coming out to be 45. So thickness can be determined by using the same equation because we want B over T ratio less than 15. So B value divided by 15 is equal to thickness of stiffness. So which is lambda R value for a 36T. This is only for the stiffness. So next is, after this, we need to check the minimum moment of inertia, whether the size is sufficient to provide the minimum moment of inertia or not. So I minimum is equal to I will show you this equation. So I minimum we are computing by this equation, JB into thickness of the web tube. So J is equal to or computed by this equation, 2.5 divided by A over H ratio minus 2. And B is the lesser out of A and H. So we can compute, and thickness of the web we also know. So we will compute the J value for the first stiffener and also for the second intermediate stiffener. And we will see that whichever is the larger, that would be critical. Because I minimum will be more if J value is more. So A over H ratio for the first intermediate stiffener is 0.52. Because for the first stiffener spacing is 1.2 meter. And for the second intermediate stiffener or the second panel, A value is 2.9. So we need to see that which equation or which panel is having the larger J value. So J value is 7.25, so we shall use this. So I minimum is equal to JB into thickness of the web tube. When we are computing this I minimum, so you can compute I minimum also for the first panel and also for the second panel. So J value for the and B value lesser out of the H. So A value is lesser than height of the girder, so B value will be 1.2 meter or 1200 millimeter. So 870 into exponent 4. So I need to check from the book, maybe there might be some correction required. And IST minimum for the second panel. So I guess I have some mistake over here. So I will check. So this answer, I guess, is 115 in the book. So I will check the calculation. So no. Sorry, this spacing is 2.9. So let me verify what is the mistake. For the second panel, we have provided stiffener at a spacing of the answer which we have computed from the book is 2.9. So I need to correct this. So actually, this value 2.9. This is a mistake over here. So quickly, let me check this answer. So 2.9 multiplied by point. So this is 145. I will make it 145. So please check in the book if there is a mistake, you can correct it. So this IST, minimum we are computing. So larger answer is coming from here. So IST minimum will be larger out of these two equations. So IST minimum will also be larger for the first panel, 870. Okay, how come we have for this equation? I will explain. So the minimum value, so moment of inertia of a single stiffener is equal to TB cube divided by 3. So how come we are getting this equation? So let me explain from here. So we want to compute the moment of inertia of stiffener about the center line of web or longitudinal axis of the web. Or if we are assuming thickness of the web 0, in other words, we want to compute the moment of inertia of this stiffener about its base. So for a rectangular, if you want to compute the moment of inertia of rectangular about its centroid, that will be BD cube divided by 12. But if you want to compute the moment of inertia about base, that will be B and D cube divided by 3. Since we want to compute the moment of inertia of stiffener about its base or center line, because we are assuming thickness of the web almost 0, so moment of inertia of one stiffener about its base or center of the web will be equal to T B cube divided by 3. So that's why moment of inertia of a single stiffener is equal to T B cube divided by 3 about the base. And moment of inertia of two stiffener will be equal to 2. To compute moment of inertia of two stiffener, we need to multiply it by 2. Similarly, we know that B over T ratio is equal to or less than equal to 15. So I'm assuming B over T ratio as a 15. So T will be equal to B over 15. Because I want to represent this equation in terms of B value. So we need to replace T value. So T is equal to B over 15. If I substitute the T value as a B over 15 in this equation, so that will become B into B cube 15 into 3. So that will become B power 4 and 15 into 3, 45. 45 divided by 2 is 22.5. So B power 4 is equal to 22.5 into IST minimum. So if we are taking the power 1 by 4 on the both sides, so if we simplify this equation, so BST minimum equal to 2.18 into IST minimum. So based upon IST minimum, the minimum B required. So we have determined two B values. The one based upon AST minimum, and second is based upon minimum moment of inertia. So that's why this expression is written in LRFD design aid. So we are computing the B minimum to stabilize the web because we require minimum moment of inertia to avoid the buckling of stiffener in out of plane direction. So after substituting the AST minimum value from here, so B is coming as 118.4. So this is B minimum. So width of the stiffener should be equal to or more than this value. So let's say we have selected the width as 125. You can also select 120, but normally it should be the multiple of 5 millimeter or 25 maybe. So we have selected as 125 mm. So we can, to maintain B over T ratio equal to 15, we can select the thickness as a B, dividing the B by 15. So I will suggest to use the second equation to determine the moment of inertia. So here he has used this equation because he has considered the both B value as a combined value. But if you are using any one of the equation, because in this equation what he has considered the bore stiffener as a one rectangular, which is having total B as a 2B. So if this is equal to 2B and this is thickness, so if you want to compute the moment of inertia about this center, which is center of the web, that will be T into the 2B cube divided by 12, or moment of inertia of the one rectangle about its base and multiply by 2. So you can use any of this equation. Either T into, let me, so either T into 2 times of the B cube divided by 12 or using this expression. So almost answer will be same. So moment of inertia is more than IST minimum. So that is okay. So we are going to use a plate of size 8 millimeter into 125 mm. Thickness of the intermediate stiffener will be 8 and width will be 125. But we need to satisfy another condition because this is the minimum moment of inertia required without tension field action. But AISC says that if we want to achieve the tension field action, so we need to satisfy the additional condition. So transverse stiffener subjected to, this is the important line. So transverse stiffener subjected to tension field action must satisfy following additional requirement. So where we want to achieve the tension field action means for the second stiffener, we need to satisfy this condition. So B over T ratio should be less than equal to 15.8. That is okay. So in that case, moment of inertia of the stiffener for tension field action. So let me, just for your clarity, I will write the FA. So that you understand why we require this. So moment of inertia required for tension field action, it should be more than this parameter. So what is this IST? IST1 is the moment of inertia for the stiffener without tension field action that we have just determined. That is this value. That is the moment of inertia, maybe from here or here, whichever you can want to use. Moment of inertia of the stiffener. So you can write as a IST1. Moment of inertia of stiffener without tension field action. And what is IST2? That is the additional moment of inertia required to satisfy the tension field action, which is computed by this equation. So IST1 is the moment of inertia of stiffener about center line of the web in pair or about the face in contact that we have determined. And what is the value here in the book given? So this value is, he has considered 115 by for the J value. Okay, no, he has considered this value that we IST minimum by the equation number 8. So equation number 8, this one. So we have determined IST minimum. So this is supposed to be 870, but in the book he has considered as a 115. So anyhow, you will check it, but I believe that this answer will be I believe this answer would be this one, 1172 or 1042. Check it, I will let you know. And IST2 minimum moment of inertia of transverse stiffener for the development of full resistance against both web buckling and field action, which is computed by this expression. So this expression is already given, we have already discussed, highlighted. So that must be determined by this equation. So in this equation, if you substitute the H value 2300 millimeter, so you will have IST2 3092. Okay, then what is the other values? So these are nominal capacity. So VR is the lesser applied shear on in any adjacent panel. So actually, first of all, I need to explain. Actually, we want to achieve the tension field action in this panel. Do not want to achieve the tension field action in this panel. So it means that VR is the lesser applied shear, whether this panel is having lesser applied shear or this panel is having lesser applied shear. So we need to check applied shear for the second panel. It is 1400. For the first panel is 1519, and for the second panel, this value is 1426. So VU value lesser of required VU in adjacent panel. Adjacent panel, the panel for which we are assuming tension field action, and for the panel we are not achieving tension field action, which is 1426. And VC1 is the smaller of nominal capacity in adjacent web panel using CV only. So, and VC2 is without CV. So first VC1, which panel, whether this panel or this panel is having less shear capacity with ignoring the tension field action. So how we can compute this? Okay, for the first panel, when we design, So when we determine the shear capacity, this is the VC value, excluding this Vn, okay? So if I divide this value 1656.9 divided by 0.9. So answer is 1841. This is the capacity of the first panel without tension free reaction or using CV only. For the second panel, so in this equation, if we are ignoring this value, because this is the total capacity with tension free reaction CV prime and also with this value. So this answer will be 0.6 if we divide this, if we are computing only this answer and divided by 0.9. So that will be the VC1 for the second panel. So second panel with CV value only will have the less capacity. So it means that VC1 will be equal to 0.56 into 250 into 2300 into thickness of the web 0.186 divided by 1000. So answer is 641.7. So nominal capacity of the second panel without CV prime or without tension free reaction is 641. So this is the answer. So VC2 smaller of Vn in adjacent web panel using both CV and CV prime. So which web panel it is having the capacity larger, including tension free reaction also. So the first panel is having the capacity 1641.7. If we are dividing it by 0.9, so answer will be 1841. Because the second panel, this one, so this is the capacity including both CV and CV prime. If you are dividing this value by 0.9, because we need just nominal capacity. So if I'm dividing this value 1943 by 0.7 by 0.9, so answer is around 2160. So total capacity of the first panel is lesser. So we are considering VC2 from the first panel. So 1641.7 divided by 0.9, it is lesser. So after substituting the values in this equation, IST, so this value will be actually, he has used as a 115. I will use why he has used 115. Let me check. So for J value 0.5, is supposed to use this value 145 IST minimum. But when we compute it, so I believe that the answer should be 1172. So I will check this mistake in the book, but I believe that IST1 should be 1172, minimum moment of inertia. So anyhow, when we computed this value, so answer is coming out to be 2657, so which is larger. So we need to recompute the size of the stiffener for tension free reaction by using this IST. So if we are using this IST, I have already explained, we can compute BST minimum, which is coming out to be 183. We will round to the upper side. You can either use 185 or 190 to maintain B over T ratio equal to 15. So the B value is, T value is required as 7 mm. So we require 7 into 185 mm intermediate stiffener to achieve the tension-free reaction. So we will replace, or this is a stiffener size. So anyhow, this size is larger than this size. But I will check, there might be some mistake. So we will provide this size. So actually this size is already lesser than this. So it is better to use this larger size. But in the book, maybe I guess there is some mistake in the calculation. Oh yes, we shall use this size because this is larger, which is more than 125. So next is we need to design the weld. So actually, when we are designing the intermediate stiffener, so for example here, so intermediate stiffener, it is to be connected by welding on the both sides. So we are welding on this side and also welding the stiffener on the both sides. And we are also providing the stiffener on the other side of the weld, which is also need to be connected by two welds. It means that at this plane, there are the shear stress they are producing in the web, they are transferred to the four weld. So it means that the total shear flow which is acting in this perpendicular direction must be transferred in the four weld, because two weld will be used to connect the one stiffener on the one side of the web, and two weld they are connecting the stiffener on the other side of the web. So AISC has given an empirical formula to compute the shear flow which is to be transferred from the stiffener to the web or vice versa. And the empirical formula is 0.0004 into H. So H is 2300. So the total shear flow which must be transferred from the web to stiffener or stiffener to the web is 0.92 kilonewton per millimeter. So for a single weld, we need to divide it by 4, which is 0.23. So I have already explained that for intermediate stiffener, we connect, it is maybe better to explain from where is the design flow. Yes. So we are connecting the intermediate stiffener. So flange will be connected with the stiffener with the continuous weld. We are providing the continuous weld over here. We shall discontinue the intermediate stiffener from the tension flange by providing a clear gap in between 4 times to 6 times of thickness of the web. But here we need to provide intermittent weld because we want to save the material. So we will provide the weld corresponding to LW minimum. So LW minimum is equal to 4 times of the thickness of the weld, which is coming out to be 32 mm. So LW should be provided more than LW minimum. So I'm not going to repeat. We have already computed the LW minimum from when we proportion the plate welder. So we have already decided as a 50 millimeter, and thickness of the weld we need to maintain the same throughout the our structure member. And weld value we have computed 1.26. So I'm not going to repeat. You can consult example 6.1. I will show you where we have already decided the thickness of the weld and the weld value. Here. So we have decided the by considering TP1 and TP2. TP1 is the thickness of our web, and TP2 is the thinner plate. So we have decided thickness of the weld, and when we computed the weld value, it came out to be 1.26. And then LW minimum is 4 times of thickness of the weld, which is 32, and we have decided length of the weld as 50 mm. So by using the same concept of shear flow, we have to decide the center to center distance or the pitch of weld. So by using the same concept, so length of the weld is equal to design weld force divided by the weld value, and this design force is in kilonewton, but we are given the shear flow. This means that if we are dividing the design force, shear force by the x or by the center to center distance, so this will become force acting per unit length, which must be equal to shear flow. So in other words, Fu will be equal to the shear flow force acting per unit length multiplied by the x value center to center distance. So if I substitute this Fu value as a Fnv into x, which is shear flow multiplied by pitch of the weld, intermittent weld. So by substituting the value over here, so length of the weld is equal to shear flow into pitch or the center to center distance between intermittent weld divided by weld value. So x will be equal to length of the weld into Rw divided by Fnv. So 50 is the adopted length of the weld value 1.26, shear flow 0.23. So x value of center to center distance is coming 274. So the maximum distance that we can provide is 274. But AISC says that we have already discussed the maximum distance, clear distance between intermittent fillet weld should not be more than 16 times of the thickness of the web and 250, whichever is lesser. So thickness of the web is 10 millimeter. 10 multiplied by 16 is 160. So 160 is lesser than 250. So it means that the clear distance between the intermittent weld is 160 maximum. So that is the clear distance, but we want to determine the pitch or center to center distance. So clear distance is 160, and if we want to determine the center to center, so we need to add half length from the one side and half length from the other side. So 16 times into thickness of the weld 160 multiplied by 50, answer is 210. So the maximum spacing that we can provide is 210. So whichever is lesser, that will be our answer. So one x value we have computed from here, which is 274, and one x value we have computed from the AISC guideline, which is 160 into plus length of the weld. So maximum pitch or center to center distance of the weld should not be more than 210. So we will round to the lower side. So we will opt the spacing 200 millimeter center to center. So we are providing intermittent weld 8 mm thick and length 50 millimeter, and length and pitch is equal to 200 millimeter. So how we can provide the weld? So just like we have to provide intermittent weld like this. So actually we have to show it by the proper designation, just like I have explained. But if you want, I will show you arrow on the both sides. So this must be 8 thickness and 50 mm at 200. Center to center. Similarly, you need to show the weld also here, or maybe also on this. Maybe on only one stiffness is okay. So we are providing intermittent weld. And at this point, we are providing the continuous weld to connect the flange with the stiffness. So this is the end of intermediate stiffener. You can solve the example given in the book for your practice. And when you are coming after your midterm exam, so I need only 2 hours to complete the bearing design of the bearing stiffener. So that I will complete during the classes or during the classes when you are coming on campus. So if someone is having any question, he can raise the hand. First of all, please raise the hand if you are present. All the students who are present, please raise the hand. Okay, if someone is having any question, he can ask me. तो सीआर ये नोट करो, सिविल इंजीनियर अली और ये मिर्जा मोहम्मद सरफराज, दे आर एब्सेंट।
सर वो मिर्जा सरफराज का कभी ऊपर जा रहा है हाथ और कभी नीचे, शायद
ठीक है बोल रहा है, ठीक है। और सिविल इंजीनियर अली ये पहले सिविल इंजीनियर बन गया है, अभी स्टेज तक के तो पास ही नहीं हुई अभी इसकी, पता नहीं इसने फेल हो जाना है अभी तो 5 सेमेस्टर में इंजीनियर पहले ही बन गए हैं। ओके, अनरेज दी हैंड, please unraise the hand, and if someone is having the question, he can ask me. So let me check what was the question of one student. He has written in the chat box. If so, I was solving the question and there was a face-to-face double channel section to be selected. I just want to confirm that whether we can use stay plate in this case. मोइन अवैस, आपका क्वेश्चन मुझे सजेस्ट कर रहा है कि आपने वो लेक्चर अटेंड ही नहीं किए कोई। मोइन अवैस, आपका जो क्वेश्चन है, आपने मुझसे पूछा कि इफ यू वांट टू डिजाइन ए डबल चैनल विद स्पेसिंग मोर देन 300 mm, तो वेदर यू कैन यूज दिस स्टे प्लेट और नॉट। तो मैं भी इसका आंसर नहीं देता, अभी आपने खुद सोचना है, आपस में डिस्कस करके बताना है कि कर सकते हैं कि नहीं कर सकते, ठीक है। एक्चुअली स्टे प्लेट दे आर ओनली यूज if we do not want, if we require the built-up section only for the strength criteria mostly, or if the gap between these section is very small, or if the gap is just equal to the thickness of the bezel plate, around maybe maximum 1500 mm, If the gap is more than 15 and 20 mm, so we cannot use with the stay plate because stay plate itself will become very heavy themselves. आप खुद सोचो कि स्टे प्लेट जिसकी जो विड्थ है गैप अगर वो 300 mm हो, आपको आइडिया ही नहीं है एक्चुअली हो रहा है कि 300 mm कितना मतलब 300 mm इज इक्वल टू 1 फीट। अगर स्टे प्लेट जिसका साइज 1 फीट 300 mm है और उसकी जो जो लेंथ है वो 75 mm है और उसकी जो अदर डायमेंशन है d वैल्यू दैट इज इक्वल टू द प्रोजेक्टेड लेग, so this plate itself will be very heavy. So in that case, if the gap is very large, then we, instead of using the stay plate, we are connected with the lacing because the weight of the lacing will become less than the weight of the stay plate. तो यही तो हमने उसका डिजाइन क्राइटेरिया पढ़ा था पहले।
सर ये तो आइडिया हो गया था मुझे कि 300 mm पे स्टे प्लेट्स नहीं लगती। मेरा ये सवाल था अगर 300 से कम हो स्पेसिंग तो क्या उसके अंदर फेस टू फेस में हम यूज कर सकते हैं, क्योंकि फेस टू फेस में वेब नहीं होता अटैच करने के लिए।
आइडिया नहीं आ रहा तुम्हें, कभी अभी इसको स्केच बनाओ तुम्हें आइडिया नहीं हो रहा। 300 से कम का क्या मतलब है? मैंने बताया कि अगर 20 मिलीमीटर से ऊपर चला जाए 15 से तो फिर आपने हमेशा लेसिंग यूज करनी, मैं ये कह रहा हूँ। आप 300 से जो कम है अगर 150 है तो वो 20 mm से ऊपर ही है। मैं बात ये कर रहा हूँ कि अगर उनके दरमियान जो डिफरेंस है, इफ दैट डिफरेंस इज इक्वल टू थिकनेस ऑफ द गजर प्लेट, देन स्टे प्लेट ओनली। इफ डिस्टेंस बिकम लार्जर मोर देन 20 मिलीमीटर, अगर चाहे वो 50 है 100 है चाहे वो 300 है या ज्यादा है, तो ऑलवेज गो फॉर लेसिंग। आपने वो लेक्चर मिस किया, दोबारा फिर उसकी एग्जांपल पढ़ो या जो मैंने अगर रिकॉर्डिंग भेजी हुई तो उसको देख लो।
ओके सर।
इस वजह से तो मैं रिकॉर्डिंग नहीं भेजता या मैं बहुत कम भेजूंगा अब आगे, क्योंकि ऑल ऑफ यू आर नॉट कंसंट्रेटिंग, इवन दो यू आर वाचिंग माय रिकॉर्डिंग यू कैन नॉट अंडरस्टैंड। तो एक्चुअली why we do not want to use the stay plate for larger spacing more than 10-20, because the size of the stay plate itself will become very heavy. So it is better to connect by the lacing. But in both cases, whether you are using the built-up section with lacing or with stay plate, we have to use end-tie plate in both cases, and must be connected with the end-tie plate, and then along the length we need to join both member by using lacing. ठीक हो गया? तो अगर डिस्टेंस नॉर्मली मैं बता रहा हूँ कि 20 mm से ऊपर चलें, आप 20 से कहते हैं 1 इंच 25 mm से, तो नॉर्मली वी गो फॉर दी लेसिंग। तो लेसिंग ज़्यादा इजी हो जाती है, यानी वहाँ पे देखना है कैन लेसिंग कैन बी अकोमोडेट और नॉट। तो इसमें ये सारा है, ठीक है। इसलिए मैंने जब आपको ये पढ़ा, व्हेन आई वाज टीचिंग, सो on you different diagram picture, actual picture I have shown you from the field, the built-up section of the bridges and towers. So I also want you to, when you are watching any steel structure, any built-up section, just observe it, whether he has made the built-up section by using the stay plates or maybe lacing. Okay, आपके क्वेश्चन से मुझे एक और आइडिया आ गया, मैं आपको एक थोड़ा सा और बता देता हूँ। If distance is less than maybe 15 millimeter, 15, just equal to the thickness of the guzzer plate, I will always use the stay plate. समझ लगी बात की? I will use the stay plate if the length is just equal to the thickness of guzzer plate. If the gap is more than 25 mm and less than maybe 2 inches or 75 mm or the 50 mm, I will use the batten. But if the gap is more than 75 mm and 100, maybe 100 से above चला गया, then I will use the lacing. So this is depending upon our requirement. So I will show you the one diagram, then I will explain. So I will show you the diagram, then you will be able to understand. So if the gap is just equal to gutter plate, then use lacing. But if the gap is less than 100 and more than thickness of the gutter plate, then it is preferred to use the like this. But if the gap is more than 100 mm, maybe 100 or maybe 150, then better to use lacing. So we have to see which one is economical. Okay, so let's see. So gap is almost maybe 4 inch or 100 mm. So he has used the batten. तो जस्ट अज्यूम करेंगे अगर यहाँ पे वो टेप प्लेट यूज करता है तो वो इस साल कितनी हैवी होती, टेप प्लेट्स का विड्थ ये होती, लेंथ उसकी यही 75 और दूसरी साइड में उसकी जो विड्थ है इक्वल, तो दैट वुड बी अनइकोनॉमिकल. तो गैप अगर 10 या 15 mm है तो टेप अगर 20 mm से ऊपर और 100 mm के दरमियान है तो बैटन यूज कर लें, अगर उससे भी ज्यादा है तो फिर लेसिंग. So that is depending upon our field condition or whichever is the economical. So you got it, Moin? Moin, you got the answer?
Yes, sir. Yes, sir. Yes.
Okay. If no one is having any question, I would like to end the class.